Okay. So Muneendra, now Dr. Muneendra, we may start now.
Yes, sir.
Yes. Open.
Yes, sir.
Just start the proceeding again.
Yes. Welcome back, everyone. We are now moving to the second session of the day. In this second session, we are going to have a hands-on session by Dr. Muneendra Ojha. So, over to you, sir.
Okay, thanks, Upin. Um so I think I had shared some of the files, and I suppose you all must have tried your hands on those files and the data that I had shared with you in the DL class 1 that I had taken day before yesterday. Today I'm going to demonstrate some of the examples that you will see will be useful for you to do this hands-on, and it creates a foundation to the neural network research, how neural network learns, how it is trained, how it functions in the forward direction and the back propagation. All these things we will see in the today's class. So starting from let's see, I have again shared this file on the same IIIT folder that I had shared with you. So anybody who has attended class must have this access to this folder, in which I have put this new Colab file IIIT2.ipynb. You can access this file, and I will again share the link so that you can um, get link. So here is the link with which you can access this folder, and in this you please access IIIT2.ipynb. With this we will be able to demonstrate the code that I'm running over here. You will be able to execute the same code. Okay, so let's start. In today's session I will talk about linear regression, logistic regression, and then I will move on to how neural network is basically nothing but a combination of logistic regressions running on every neuron. So just to start with, let us understand what supervised learning is. In supervised learning, we are given input examples along with their label. Okay, these labels, if they are continuous values belonging to R, this function f is called a regressor function and the activity is called regression. If label y is discrete and you are able to divide it into classes, discrete classes, this activity is called classification and the function is called a classifier. If it is two class, then binary classifier. More than two classes, then it is called multiple class classifier. Okay, and the activity is called multi-class classification. So the idea of supervised learning is that every time we give it an example, along with that example we provide a label as well. Okay, so just like a supervised learning we do in the classes, we teach our students and then we give them examples also. So we are there to train them under supervision. So all the training happens under supervision. So why I'm talking about supervised learning, because neural network research is mostly with the fundamental research, that fundamental work that is going on is mostly supervised, although there are a lot of unsupervised parts as well, which you will see in the classes which are yet to come. A lot of unsupervised part is also there, but the basic fundamental concept is under supervised learning. So once you have the foundation, then you can move on to unsupervised deep learning as well. Let's see, when we do linear regression, we are given these examples in the rectangular data format. X, all these X's are the inputs, and then Y's are the labels that are provided to us. Our job in linear regression is to find when this R or D is given, we have D-dimensional data, we have to find out a label that is a real value. And in this example, in this figure, as you can see, all these red dots are the samples, actual sample. Our in linear regression, our job is to find out a line or a linear curve which is able to approximate all the data most efficiently. When we say most efficiently, that literally means that this line has the minimum error. Okay, how do we find out the error? This difference is the error. You see the difference between red dot and the actual line on the y-axis. This difference is the error. That is the error. So sum of all errors is minimum for this line. Then this line is the best regressor function. If it is two-dimensional, then we get a plane. If it is one-dimensional, we get a line. If it gets more than 2 dimension, 3 dimension, then we get a plane which we call as hyperplane. So a generalized linear regression model seems like this one, in which you have a value, that is, first one is the bias, and then for every feature, that is x1, x2, xj, xd, suppose we have d features, we have a weight coefficient. These weight coefficients indicate how much is the importance that should be put on a particular feature, how much preference we should give to a particular feature. And in generalized format, this is the equation of a linear regression model. So once we have the linear regression generalized model, our objective over here is to find these weight values. Most of the time you would observe that these weight values are represented as beta, and then this W naught is represented as B. A lot of different books have their own different notations. Like over here, you see in this example, I have given fxi as a function of the weight matrix, because all of these weight values are weight. You can have a weight vector W, and then a dot product of wt with the x. Okay, this x is our uh, d dimensional vector, and the final we have a bias value. So this W naught can be treated as a bias, and rest of these coefficients are part of the W weight vector. Our job is to have this in matrix notation. We can simplify it as fx is equal to x dot W, where x is the set of um, our known data set, the data matrix. Okay, so x is our data matrix, weight is our weight matrix, and b is the bias. So this is the generalized form of a linear regression model. The whole learning linear model is summarized as learning the weight coefficients W. So our objective boils down to learning W. Okay, because you see in this equation, if I ask you what is unknown to you, this is equation of the linear regressor, right? So do we know this line? Do we know the equation of this line? We don't know. It is just a at the very beginning, this is just an approximation that okay, we let us start W naught with some value, W1 with some value, W2 with some value. We randomly initialize W values. Then we gradually keep on changing our weight values, so that at some point of time, these weight values, when converged, we say that our model has converged. So when the model converges, the learning converges onto some final W value, then at that point of time, this equation is created, and this equation is a culmination of various W values that have been learned throughout the learning process, throughout the training process. So in this equation, the only thing that is unknown to you is W value. X is known to you, fx is the resultant, and y that is the target label, because y is this example. So y label is already provided to you. So since y is known, x is known, what is unknown for this equation is the set of W values. So our whole learning boils down to learning the weight coefficients W. Okay, for that, how do we learn it? What we do is, as I said, the objective of this linear regression is to find out that line or that linear equation. Like this two-dimensional, we have a linear plane. So our objective is to find out a linear equation which gives me minimum average error. Okay, minimum average error. So minimum average error means what? I will sum these error terms. So how do I find out the error term? You see, this is the error term. So suppose this is your sample yi label. Okay, for a given x, this is the y. This part is y. Let me annotate over here. So this is y. This is y. Okay, while your predictor, that is your linear regressor, is predicting it to be over here, because this is the equation of line, and line says that for a given x, this is the point corresponding to the line. So this part is the error. This part is the error. This part is the error. Now I take a sum of all of these errors. So this error, right? This error, I take a sum of all of them and do an averaging. So I mean, I have got 5 errors over here. So I will add all the 5 errors and divide it by 5. Of course, not exact sum, but what you can do, you can take an absolute value sum, or you can do a square sum as well. Okay, so what we can do, so yi is the absolute value that I want, and fxi, this is the fxi value, is the obtained y value, obtained level. So what do? We take a subtraction, then we square and sum all of them together. So when I sum, I have to take an average, so I divide by n, and this becomes my mean of squared error. Okay, this is called mean squared error, MSE, mean squared error. So this term is mean squared error. And you would ask that if I have to divide by n, why I divided by 2? Just we divided by 2 because we have to differentiate this function at some point of time. So when I will differentiate, this 2 will definitely come over here. So this 2 and this 2 in denominator should get cancelled. So I have a simplified expression. That is the only reason I divide by 2. Otherwise, nothing special about this 2. So idea is to get a mean squared error. So this is the error. I have squared it and then taken mean of all the errors. That becomes the mean squared error. Now, if I'm able to minimize this R, the risk or the loss or the cost function, this cost function, if I'm able to minimize, then my equation will of the line will give me the least error approximation of this regression function. So what happens is that first we initialize this equation. We initialize with a random set of weight values. Fine. And then we calculate the average loss or average cost. So we calculate this cost function, and this cost function we try to find out the minimum. We try to minimize this cost. So suppose if I have a cost function like this, since this is a square quadratic function, it will be a parabolic curve. So suppose I have this equation of r like this. Okay, this is equation of r on the basis of different w value, because w is the weight coefficient, it depends upon w. So on the basis of w, this is the equation of the r, the cost function over here, this cost function. So my objective is, suppose I initialize some weight value such that initial error is over here. My objective is to bring this error down towards this value. So this, I think this is minimum. So I want my error to be minimum. Okay, so I want my error from this point, initial this point, to come down to this point. If you are very lucky, then whatever value of weight value you have initialized, whatever values of weight you have initialized it with, is actually at the very bottom, but that doesn't happen. So what we do, we initialize weight values randomly and then calculate this cost function and then try to minimize the cost function. That is the basic idea of gradient descent. So if you know gradient descent, you will understand that my base overall idea is to have a cost function and then gradually calculating the gradient, I want to come down towards the minimum error value. Okay, that is my objective. Okay, so what I have done, I have created a linear regressor, an approximate linear regressor function which looks like this. In general terms, it looks like w naught plus summation j equal to 1 to d wj xj, and this is the generalized format. And I have a cost function as well. Cost function is given by mean squared error. Now my objective is to start from somewhere, okay, and then gradually, so in this I will start from somewhere, let's say here, and then I will gradually move from here to here to here, and then subsequently I need to converge onto this minimum error. That is my objective. So if I suppose on this error curve I want to move from here to here to here to here to here, somewhere like this, I want to converge onto the minimum error. And minimum error is this error curve is a function of all the parameters, w's or beta or whatever term you use it to identify. Okay, I normally it is preferable that we use similar notation. Okay, so if I start with w, I should be calling it w all the time. But that is, life is not ideal. That is not the case that everybody follows the coefficient as w. In neural network, you will find the coefficients to be referred to as W, while in statistical term, you will find them to be referred to as beta, like the best, one of the best books of uh, statistics, the fundamentals of statistical learning by Trevor Hasty. You will find that they refer it as beta. The coefficients are referred to as beta. These coefficients are actually the parameter. So ultimately, either it be W or it be beta. It's a matter of learning these parameter. So these kind of algorithms, like it be linear regression, logistic regression, neural network, all of them fall into the category of machine learning, which is called parameterized learning algorithm, parametric learning algorithm. So objective of these algorithms is to learn the parameters. So these are the parameter that we want to learn. And the objective of me keeping W somewhere and beta somewhere is for you to understand, if for my students to understand that any notation can be used in the literature, but they must be able to understand the inherent concept. So the cost function, so this is a generalized equation. So if I take one variable, the linear regressor function becomes fx equal to beta naught plus beta 1. It could also be called as mx plus c. Remember, the equation of a line is in our coordinate geometry. The equation of line is normally referred to as mx plus c, where m is the slope and c is the intercept on y-axis. So this is c, intercept on y-axis, and m is the slope. So by mx plus c, and in one variable, beta 1 could be called m and beta naught could be called c. So equation of this line becomes mx plus c. If this is cost function yi minus fx I square, I can put beta naught plus beta 1 x in place of fx, and this becomes yi minus beta naught minus beta 1 x square, and then this becomes the cost function. To get the minimum cost, our objective is to find the set of beta naught and beta 1 that minimizes this cost function. Okay, so everything converges down to finding the best set of beta naught and beta 1 values. Okay, so there are a lot of mathematics that has gone into it. If I have to minimize something, we perform a partial differentiation with respect to first beta naught, and then with respect to beta 1, if we do del r upon del beta naught equal to 0, we need to find the slope. You are must be very clear about how do we find the slope of a, how do we find the minimum of a function. So if I have to find the minimum of this function, we differentiate. The first order differentiation gives me some expression, and then we equate it to 0 to obtain the coordinate of those points where this inflection point is present. So we differentiate with respect to first beta naught and then equate it to 0 to get beta naught expression that is represented in equation 2. Then again we differentiate partially with respect to beta 1 equated to 0 to get an expression by combining 2 and 3. By plugging beta naught and beta 1 together, we can find this complicated expression for beta 1, and similarly we can find the other one for beta naught as well. Right? If you have more than one feature, of course this equation changes. Instead of just beta naught plus beta 1 x, you will have beta naught plus beta 1 x1, beta 2 x2, beta 3 x3, and so on so forth. So the job would be to find beta j that minimize this cost value. Okay, minimizes the cost value. Now When there is a single input variable x, the method is referred to as simple linear regression. When there are multiple input variables, literature from statistics often refer to the method as multiple linear regression. Now let us see an example. In this example, we are trying to build a linear regression model from the ground up using NumPy only. Okay, so let me connect my Colab file to Google backend. I think everybody is able to access this file. Guys, can you access this file and are you able to run this along with me?
Participants, you may respond if you.
You may either write on the chat box, or you can tell me by unmuting.
Yes, people are writing on the chat.
Yes, sir, got it.
Some is saying yes, some is saying no.
Somebody
Majority is saying
no.
yes.
Okay. So,
Majority is saying yes.
okay, Miss Sapna, she says no. So you can access, Miss Sapna, you can access. I have actually shared it on Google Drive and I have shared the link also. So you can access it. This is the folder. I have shared the link of it on the chat. You can access that. Okay, where was I? Yeah. So see, so I will start from here. First things first, we need to import all the packages. Then I need to mount the Google Drive. Okay, mounting the Google Drive means I am connecting my Google Drive over here, and as I had shown you previously also, I need to go to this link to authorize myself. First identify the email with which I want to connect, and then authorize myself to access the file. This is the authorization code. I copy it and then I come back and paste it over here, press enter. Now the authorization code is entered. It should mount my Google Drive in this Colab file. Great, drive is mounted. Okay, so you see I can access all the drive. Right, so triplet TNR, I think, okay, 1 second. Oh, I actually gave wrong email ID. I am actually running it with just a second. Let me just do a factory reset, remount the drive because I am. Yeah, let me reconnect. I have these files on my personal email ID, but I gave it access to my official email ID. So just a second, let me just come back to you. So I will mount it again. Okay, I think somebody is having some problem. We should address that. Just a second. I am seeing some messages, but let me. Yeah, drive is mounted. Now let's see what the people have to say. Some messages are there. Okay. Miss Shabana says that I have low internet connectivity and can't open the files. I have already requested the recording so that I could practice at my. Okay, no issues, no issues. Okay. So Kashmir is still 2G internet connectivity since abrogation of article. You will get 3G, no issues. Okay. So
Sabana, it will be shared to Sabana, it will be shared to you on email and also. So
yeah,
don't worry for
no
that.
issues.
Yes.
Okay. So it's just for your own help that you are able to access. If you're not, then you can access the recordings as well, no issues. So you see, so my drive is mounted. Now I need to access the file. If I access the file, I'll have to go to drive, my drive, and then I have IIIT folder. In this folder, I will need access to simple LR. So I'll just copy the path and then paste this path over here so that I am able to access the, sorry, it should be from here to here. Right, this is the correct path. Now I will run it. And gen from next is not defined. Okay, it has imported everything, still it is not included. Why? Acha, acha, acha. Okay, sorry. I actually did a factory reset, but after that I didn't run the imports. So, right now I have to. Now, see, this is the data set. Okay, it's a random scattered data set that we have created. This file is over here in this simple LR linear regression data. Okay, so you can access this file, and when you access this file, I have displayed over here. So it is just plotted with using simple from np.get from gen from text. This is the CSV file. Using delimiter, we have read the content into points. ND array. So now this using this array we can get all the points on 0 and 1 becomes the label. So y is the label, 0 is the data set, and now I have plotted. So this is the plot. Now you see the equation for reference y equal to mx plus c, as I was telling. So b, I'm shifting from c to b because I wanted to let you know that b is the bias term. Okay, so let's say initial rate is 0.001, initial bias is 0, initial slope is 0, number of iterations 10. So a very simplistic starting point. So what I do, I compute the cost, and you know cost is equal to y minus the function mx plus b, okay, squared. So what I've done for all the values in the length point. So what are points? Points are these values, right? Points are all these values. So for all samples, I calculate the cost as a total sum of all the errors, squared errors. So this is sum of squared errors, right? This is in this for loop, I'm getting sum of squared error. And when I divide it by n, I'm doing a mean of sum of every mean of squared error. Okay. Okay. Are you not able to access this? Hmm. I think this has access to everything. Anyone with the link can access this folder. So I think these files are accessible to everyone because anybody with the link can access this. Let me just do it. Share with people. Share, yeah, change, copy link. Anyone with the link can access this folder. So everybody is a viewer, right? Let me make editor. All of you with this link are editors, so you can see. Fine. Okay. So we have calculated mean of squared error in this function. Now we perform the gradient descent run. Okay. Gradient descent means what we are doing. We are doing the gradient, step gradient, and with every iteration we are inching closer towards a smaller error. And then in gradient descent, what we do, we have what is gradient? Gradient is nothing but minus alpha del of r upon del of w. Okay, the parameter against which you want to calculate. So this is the gradient term. So gradient term means you have to differentiate the cost function. If you differentiate the cost function, this is the kind of expression you will get: minus 2 upon n x into y minus fx. Y minus fx, this is mx plus b. So this is the kind of expression you will get if you differentiate the current cost function. So what I have got two parameters. So we differentiate it with respect to two parameters. First with m, the slope, and second with the bias value. So m gradient and b gradient. And remember, all these gradients of all these parameters must be calculated simultaneously. So for every point in this, every point in the input. Okay, there is a question. Shubham, what is the problem? It is asking for authorization code. This authorization code is your code. You have to copy that. Okay. of how to mount it. Otherwise, there is no authorization code. Authorization code is something which is related to your email ID if you need to mount it. Okay. First,
Okay,
you copy that and get it in your drive. You can't access my drive. You can't get authorization code to my drive. You copy the content to your drive and access the authorization code.
okay, sir.
So so this is the gradient that we have calculated with respect to every parameter, and then we update the gradient to B. So when we update the gradient, the new weight value should be W new. Suppose W new is equal to W dash and old W is W. So W equal to W minus alpha del R upon del W. This is the weight update formula when we perform the gradient descent. Okay, and then it will return the updated values of B as well as M. So this is the function. Now let me run them. If I have not, yeah, I have not run this, then I'll run this so that everything functions as expected. Now here. So I run the gradient descent runner to get the optimized parameters of B. So let me run it. So these are the optimized values. Okay. Now I will plot, and this is the plot of cost. Okay, the cost per iteration. So number of iterations 10, and the cost started with 5 more than 5,000, somewhere around.
Muneendra, Dr. Muneendra, just check out this chat box. They are writing something.
Okay. Manas is saying that it is triple ITO to. Okay, sir. 1 second. Let me just. If you don't have, let me. I think I had downloaded it. So, how do I share on this? Do we have a WhatsApp group where I can share these, sir?
They have.
If I give it to you, can you pass it on to candidates?
Sir, I'm just
Yes, I will pass on. Upendra, I'm just forwarding, then you just pass on.
yes.
Fine. I think now people can get. Okay. Great. Fine. So this is a graph of how cost is decreasing from the first iteration up to 10th iteration. And then if I try to plot the best fit that we have obtained, this is the line that we have obtained after 10 iterations. So initially we started with nothing. Okay, initially B was 0, M was 0, then learning rate was this. So this is after few iteration, after 10 iteration, this is the line of a linear regressor that we have found out, and after 10 iteration we can of course carry on many more iterations, but the idea is after 10 iteration I have obtained an approximate regressor function, an approximate regressor line that is able to approximate the minimum error among all these samples. So these errors, average of all the errors is minimized. Okay, we can further minimize if we run for more iteration. So you get the basic idea of what is happening. So idea is first to create an approximate function and then create the loss function, the cost function. So when we have the cost function, we try to minimize this cost, and while minimizing the cost, the new beta values, the new parameters that get updated, update the equation of this line. equation of this hyperplane. So if you have more than 3-4 feature values, then that plane, the linear, it will still be linear, but then it will be called a hyperplane. So you get the approximate equation of that hyperplane, which is able to represent these points in the most least error format. Now, if we can use the scikit-learn library to perform this again. So for this scikit example, I have taken the diabetes dataset. Remember, yes, a day before yesterday, I was talking about the Pima Indian dataset, diabetes dataset. This you can download from the scikit-learn datasets library also. So if I just run it, okay. So we split the target training and testing set, split the target into training set. I think I did it 2 times. Okay. Anyways, split the data, right? So split the data into training and target, and split the target into training and testing sets. So this done, then I do the create linear regression object. So we create a linear regression object through the linear regression function provided in the scikit-learn. Okay, and we perform the prediction. So in this, if we have to print the coefficient, this is the coefficient value, okay, and then coefficient of determination 0.47, mean squared error is this. If we plot the output, you see, so for a small set of data set, this is the output which is able to give you an approximation of the whole distribution. Although I understand this doesn't look like a very good very good approximation, but if we run for more epochs, run for more iterations, we will get a better representation. Now, in linear regression, we are creating a linear function, okay, fx equal to w naught plus w1 x1, w2 x2, w3 x3. This is an equation of a linear function because the degree of polynomial is 1. However, there are cases in which linear function is not able to perform the classification in case of non-linear distribution. So if linear function cannot perform the classification in case of perfect classification in case of non-linear distributions, then we need non-linear functions for this job. Okay, so logistic regression actually moves one step ahead. And logistic regression, although the name says regression, it is a classification technique. So logistic regression, what it does, it takes the same linear function and passes it on to a non-linear function, that is a sigmoid function, and then that becomes an in total that becomes a non-linear function. So we will again do this logistic regression with the help of the breast cancer data that I have shared. Let me copy the path of it. So over here you see I just copy the path. My drive is already mounted, so I will need to run it to read the uh, so I'm using pandas over here. So see, I am giving a lot of different flavors to you of the coding example, and you all these codes can be used. Okay, it's not, you should not get confused why I'm sometimes using numpy, sometimes I'm using scikit-learn, sometimes I'm using pandas. All of these are different ways of doing the same thing. So since I cannot teach everything, nobody can teach everything in a given FDP. So these examples actually help you understand that, okay, the same thing, if I have to read a CSV file, I read using NumPy through gen from text, and again, I use it, read it using the pandas library over here. So these are different ways of doing the same thing. So logistic regression done. Let me read it over here. I think it is red, and I find out the shape. I reshape everything, okay, to be 1 1, and now I have to split data set into training and test data set. That's okay. Now I train on logistic regression using scikit-learn. if we calculate the confusion matrix and accuracy, so see, this is the confusion matrix and accuracy, test accuracy is 94%. Fine. So on this breast cancer data set, the accuracy is 94%, and it's a very simple model. What happens in logistic regression is that if I could explain in terms of equation, okay, I will explain in terms of equation, but you will have to wait for few moments. I will actually take help of something. Yes, yeah, over here. Remember the linear regression function that I had created? That function was, the generalized equation of that function was f equal to w naught plus summation wi xi. Okay, wi xi, right, plus b, of course, plus b. So if this is the equation, I mean, not this, if this whole is the equation of, let's say, let me call it the f1, and this is equation of linear regressor, and if I call this f1 equal to z, and I pass this z to this sigmoid function as here, so sigmoid function is 1 upon 1 plus e to power minus x. Sigmoid function is given like this, and the equation of sigmoid function is like this. It minimum value is 0, then crosses the x-axis on origin on 0.5, and then it gives a s which is equal to 1. This is 1 and this is 0. It's a s function. My drawing is very poor because I have to use the mouse at the moment. So this is an s function. Minimum of sigmoid value is 0 and maximum is 1. So you see, I have this linear equation like this, linear regressor, and this output of linear regressor is actually passed to sigmoid function in terms of z value, and z value is called legit. Z value over here is called, z is equal to legit. Legit is equal to summation of all wx wixi. So this is the summation of it. So this is being passed to this sigmoid function, and output of this sigmoid function now is the output of logistic regression. Okay, so logistic regression is nothing but output of linear regression being passed to a logistic function or sigmoid function. Sigmoid function is also called as logistic function. That is why the name logistic regression. So the output of logistic function falls between 0 to 1. 0 to 1. And if you notice, the probability value also falls between 0 to 1. 0 to 1. Okay, probability value also falls between 0 to 1. So logistic regression is basically used as a classifier in which if it is greater than 0.5, we classify it to belong to class 1, and if it is 0.5, then we declare that it belongs to class 0, and thus we do the binary classification using logistic regression. Why I'm discussing linear regression and logistic regression at this moment, and as I have shown you in this demo, that both of these are working, and with the very simple uh, using the numpy array we demonstrated logistic regression, then we linear regression, then we performed linear regression using scikit-learn, and then using scikit-learn I demonstrated you the logistic regression in which we get the accuracy of 94%. All these actually create a fundamental for neural network research. Okay, in neural network
Also,
research,
Dr. Munin,
yes sir,
okay. If all the participant, if anyone have any query for discussion at this moment, they may unmute and discuss for 1 or 2 minutes before. Yes.
yes, very good point, because now I'm shifting from the fundamental and I'll be using it to create the foundation of neural networks. So if you have any questions,
Yes.
you can ask me.
Yes, so here for the discussion point of view, even for the collabs and any issue if you want to discuss, I would like to request to the participants, you may unmute at a time one and discuss if you have.
Okay, I think no.
Anyone have any question? Am I audible or not?
Hello, sir.
Yeah.
Yes.
Sir, in logistic regression, the accuracy is 94%.
Mm-hmm.
Sir, how is this accuracy come, sir? I'm confused with that.
Oh, I'm just using the predicted value and test value. You see over here, we have divided the data set into training and testing data set, right?
Yes.
Actually, I did not elaborate it as much as I had elaborated linear regression because that you reusing those things. And in last class also, I had told you that if we have a data set of say 1000 samples, we divide it into 80-20. So the 20 we keep for testing. So here what I'm doing, I'm dividing my data set into X train, X test and Y train, Y test. So when I have done the training, I call the CLF fit function, right? So CLF is the object, logistic regression object using random state 0. So we perform this logistic regression. In logistic regression, while training, we pass the training X and training Y. Fine. So we train on the trained data set. And after training, we assume that this object has been trained. The CLF object has been trained. Once it is trained, then I can predict using the test data set. Okay. So Y prediction is the result of when I pass the test dataset to my clf.predict function. So CLF is the object, right? The linear logistic regression object, and this object, while calling the fit function, I have trained it, and with the once CLF is a trained model, logistic regression model, now I can use this model to predict. So using the predict function, I can Using the predict function, I can predict on an unknown example. So what is unknown example to me? The test dataset that I had kept over here safely, the Y train Y test. This dataset I will use to test whether my CLF is giving me correct prediction or not. So all the test X I will pass and I will create Y prediction. Now I will compare Y prediction with Y test because Y test is the actual label and Y predicted is the label that is predicted by my model. So calling this confusion matrix function, I will be able to match whether predicted label is same as the actual label or not, and then we print the confusion matrix. Accuracy also I can calculate by using the actual label Y label and predicted Y label, and that comes out to be 94%, right?
Okay, sir. Yes, sir.
Okay.
Okay.
Yes, sir. I
So
have a
any further,
question.
if anyone have
Yeah,
any
yes, sir.
query?
I
Okay,
have
go
one
ahead.
question. Sir,
Yeah.
what
Yes,
what
yes,
do
yes.
yes, yes, sorry, sir, what do you mean the random state by random state equals to zero? Suppose I am giving random state 1, 2, 3, then there is some difference.
Yeah, this there will be difference. It is a seed value that we start with. Okay.
Okay.
So first we need to initialize our weight value. So we have to fix the random value. So it is seed value with which we start. Random, if you change the zero value, it instead of zero, you will get different value. So for the purpose of reproducibility of the same result, we fix the seed, random seed. This seed fixes that.
So, sir, if I change this 0 to 1, then the accuracy will be more or less.
It doesn't matter. No one can
Okay.
predict that. It's
Okay.
just random
It may be less
initialization
or it
of
may
weight
be more than
values.
this one.
It may be less, it may be more, but no one can predict it.
Okay, sir.
Okay.
Thank you, sir.
So then we perform now
Okay. So
from here
now
I
no
will
one. So we, Dr. Munir, you may move on as per
okay sir.
the
Okay
schedule
sir.
now.
So now I move on to neural network, and then a neural network, you might have some basic idea that neural network is actually a network of layers. Okay, it has an input layer, then a set of hidden layers, and finally an output layer. what happens in input layer? Although I'm calling input layer as a layer, input layer is not technically a layer. Okay, it is just a mechanism of providing input. So in input layer, we have all the inputs in a vector form. Then in hidden these layer structure, we have the actual computing layers. So these layers, it is called hidden layer because previously people treated neural network as black boxes in which they were concerned with how input is presented and how output is obtained. So they were not concerned with how the computation happens inside this within the input and output. So that was hidden, and that is why it is called hidden layer. So these are hidden layer, and how actually neural network performs can be represented very beautifully using this animation, in which suppose I have a set of handwritten digits. So you see 2 is presented as a set of pixels. So this is 28 by 28 image size. Okay, 28 pixels in horizontal and 28 pixels in vertical. So total of is 784 pixels are there, and all pixel values, since this is a grayscale image, so it is a monochrome. So you get a single value, single channel, and pixel grayscale value is presented over here in every node. So every node, every circle you see over here is actually presenting one pixel value, and since it is 28 by 28, it counts to 784 pixel values. Now these pixel values are passed on to next layer. How? Every node of the input layer, you see if I mark it like this is one node. This node is connected with all the nodes of next layer. I'm missing some of them for the lack of space, but you see as per these markings, the white markings, you can see the web kind of a structure you can see over here, right? All these edges represent that every node of input layer, every node of input layer is connected with every node of the first hidden layer. This is the first hidden layer. Fine. So every node of input layer is connected to every node of first hidden layer. This mechanism, this connection mechanism is called fully connected. Just like you have a graph and that graph has all the nodes connected to all other nodes, then that graph is called fully connected. Similarly over here, this is called fully connected layer or dense layer. Both of these FC, sometimes you will see that it is represented as FC, fully connected, and technically we use the term dense to call a function. We call the function dense to represent a fully connected layer. So this is a fully connected layer. Now all the nodes of this layer are connected to all the nodes of second hidden layer. Fine. And similarly all the nodes of second hidden layer are connected to all the nodes of third layer, which is also the actually the output layer. So this is output layer.
Sorry to disturb you, sir. Sir, can you explain once again this one, sir, the working of neural network?
Yeah, I'm actually coming on to that. So
Okay,
what
okay, thank you,
happens
sir.
is input is presented at the input layer such that every node represents one pixel value of this image, and then these values are passed on to every neuron. Okay, every neuron. Now every neuron performs some computation, and I am saying every neuron performs computation. These are not neuron. Okay, these are not neuron. They are not neuron. These are neurons. So every neuron performs some computation and then produces an output. This output is again passed on to all the neurons of uh, next layer, right? So the output of this neuron is passed on to all the neurons of next layer. Similarly, these neurons perform some computation, and then output of these are passed on to neurons of all the neurons of next layer. Okay, this is how every neuron functions. So see, although it looks like a layered structure, if you go deeper into a layer, every layer is composed of hundreds of thousands of neurons. Okay, and neuron is the fundamental computing unit. So layer doesn't do anything. Layer is a computing unit, a collection of computing units. It looks like a layer, however, the just a second. Okay, so these layers are actually composed of individual neurons. If there could be hundreds, there could be thousands neuron per layer. So whatever this layer represents is culmination of what these neurons produce as output. Okay, so layer is not the computing unit. These neurons are the computing unit. Fine. So you could assume this neural network to be a layered structure, and then there's our layer, input layer, hidden layer, output layer as a broad bird's eye view. When you go deeper, you see this kind of a structure in which input is presented at input layer. Then these neurons, the data is passed in the forward direction. Okay, so this data moves from here to here in forward direction by computing by the mean of individual computing units. Now, what are these computing units? Okay, so first I give you this bird's eye view, the layered structure of a neural network. Then I gave the slight introduction into what is this web of computation, and then I move into an individual computing unit, that is the neuron. So what happens in layer that you observe over here, but what happens in neuron, the entity which is actually calculating, can be explained with this diagram. See, in this diagram, you see this blue region, this blue rectangle is the set of input that is provided. Along with input, you have one weight bias value as well. Okay, so what happens is that all these inputs, they come, okay, and there are edges. There are edges over here. So every node is connected to every node of the next layer through edges. Okay, these edges, of course, they are edges. We represent them as edges, but they are not actually edges. How would you create an edge in mathematics? Okay, these are just representations. So this representation says that there are connections. What does it mean by connection is that suppose these are input values. These input values are being passed onto this neuron. So this red rectangle is the neuron, the mathematical model of neuron. What is happening over here is that this input is this input is passed. It goes through an edge and comes to neuron. On this edge there is a weight value. For this I call this weight value as B. Then second input again follows this edge and goes to the neuron. On this edge there is a weight value called W1. Okay, then third input again follows an edge and goes to this neuron, and on this edge it has a weight value W2. Then this input X3 follows an edge and goes to this neuron, and this edge has a weight value W3, and so on. And finally Xn follows an edge and goes to this neuron, and this edge has a weight value Wn. Now I will remove my markings so that you see the clear image. So you understand that every input is being passed to this neuron by following its corresponding edge only. Okay, this edge only. And every edge has got a weight value. This, since this is biased, this is called B. Otherwise, remaining of them are called W, representing a weight value. And when it says, you see this symbol summation over here, then what is actually happening over here is that this portion of neural network is performing a weighted sum. Weighted sum means first one 1 dot B. Okay, so the first input 1 is multiplied with its weight value B and added to second input multiplied with its weight value. So x1 w1. Okay, then added to third input x3 multiplied with weight value. So x2 w2 plus x3 multiplied with w3 plus dot 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 dot. Finally, xn wn. This is the sum that is being calculated at this point, which we call as weighted sum. Okay, you all know what is weighted sum. Weighted sum. This is a weighted sum. Doesn't it look like a linear regression function? Of course it does. It does in a way that this is, if I call it as z, if I represent this expression as z, z could be written as b plus summation wi xi, and voila, this is the equation of linear regressor, right? So here, up to this point in a neuron, linear regression is working and a z is created. This z is passed on to an activation function, and if I say that this activation function is a sigmoid activation function or a logistic activation function, then this value z will be passed on to sigma function is sigmoid function, and it will become 1 upon 1 plus e to power minus z, and immediately it becomes a logistic regression. So here I am having a linear regression up to this point, or kind of linear regression, and at this point, as soon as I pass this z to a non-linear activation function, for example sigmoid. Why I'm taking this example of sigmoid? Because in earlier research, sigmoid function was the go-to function for all the neurons. So still sigmoid function plays a very important, very crucial role for neural network uh, action mechanism. So this activation function is sigmoid function, and this gives me an output of sigmoid of z, and this is actually this value, right? This value, and that is the output. That is the output of a neuron. So can't I say that a neuron is actually producing a logistic regression output for all the input that is being given to it? Yes, I can see, because this is how mathematically I have shown you that whatever happens inside a neuron is nothing but a weighted sum being passed to a logistic function, the activation function, and the output, if this function is logistic function, the sigmoid function is also called logistic function. So if this function, activation function, is a sigmoid function, then output of a neuron is nothing but the output of logistic regression. Okay, having established that this output is logistic regression, log regression, logistic, no, I will not call it log regression, logistic regression. I can say that if I, this is a zoomed in, okay, zoomed in version of a neuron. So I can say now that all these nodes that you see over here are, what are they doing? They are doing a classification. Okay, as I told you, logistic regression, although it is called logistic regression, it is actually performing classification. So every neuron is doing what? Up, every neuron is actually performing a logistic regression. And as soon as it does a logistic regression on the basis of weight values and on the basis of input that it receives, it activates itself or remains deactivated. What does it mean by that? Idea of logistic regression is to perform a binary classification. Okay, logistic regression, in this I perform a binary classification. If I classify my input on the basis of logistic regression to be 1, then I will activate myself as it is green. If I decide that okay, the input and weight combination doesn't give me sufficient reason to classify as 1, then it will be classified as 0. And if it is classified as 0, okay, or for 1 it is activated. Let's say for 7, what happens? Okay, for 7 also it is activated. Okay, let me shift here. Okay, so now for this I remain deactivated. So this neuron remains deactivated. Now every neuron has to make this decision because every neuron is running a logistic regression function, logistic regression model inside themselves. So every neuron makes a decision whether to activate itself or remain deactivated. And when this happens in whole layer, I see a vector of 10101010101010 something. And as soon as I see a vector of 10 values, that vector of 10 binary values give me a lot of information. Okay, huge amount of information. And with that information, I pass that whole information to the next layer. Okay, now this next layer again has the same set of neurons. Okay, all those neurons will again, on the basis of input that they are getting, decide for themselves. हर न्यूरॉन अकेले डिसाइड करता है whether it has to activate itself or remain deactivated. If a neuron decides to activate, it will activate. If a neuron decides to remain deactivated, it will remain deactivated. Like these three are remaining deactivated. And on the basis of all these neurons, I create again a vector of layer. This layer has now become a vector of 1010101010. Now this 10 vector, binary vector, is again passed over here, and then it has a an output of some neurons activating themselves and some neurons remaining deactivated. On the basis of this output, I have to decide, like suppose this is image 2, image of 1, then this neuron should activate only and remaining should remain 0. Okay, so if that is the case, my output should look like, suppose it is 7. So for 7, the output vector should look like this: 0 0 0 0 0 0 0 1 0 and 0. The output vector should look like this. But who knows that all the computation is going to give me immediate result? No, it will not give me immediate result because W values are not sufficiently converged, right? What do we mean by convergence? Remember, in linear regression I had told you that we need to find the most suitable set of parameters such that my error is minimum. So this is our expected output. This is expected output Y. But your output, your neural network output will be something different. It will be 0.1, 0.2, it might be 0.9, who knows, 0.4, okay, 0.4, 0.2, etc. dot 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 etc. So now what should I do? I should take a subtraction. I will remove it. I will take a subtraction of errors, okay, of errors, and then I will again perform this sum of all errors, to calculate my mean squared error function. Fine. When I have mean squared error function, I will again apply the gradient descent to update weight values on these edges. And where are the weight values? Remember, the weight values are the values which we can update. Only we can play with weight values, nothing else, because target is given to you, input is given to you. Fx is calculated by this model. So nothing is under your control except these weight values. So these are the weight values which are the only thing which you can play with. आप सिर्फ वेट वैल्यूज को ही पकड़ के इधर उधर कर सकते हैं, आपके पास और कोई चारा नहीं, और कोई भी चीज स्ट्रक्चर भी एक बार ऑफ द न्यूरल नेटवर्क, वंस दिस स्ट्रक्चर इज डिफाइंड, यू कैन नॉट play with that structure. Okay, so the only thing you can change is the set of weight values. Okay, so to find the best set of weight values is to train the neural network. That is what we do. And again we have set multi-layer of neural network. So you see over here multi-layers of neural network. These layers don't really need to be sequentially like this, they can be arranged in a random order also. But since I'm not getting into recurrent neural network, I am telling you that it is kind of directed acyclic graph. I'm not telling you to create cycle at the moment. I don't know whether you have studied recurrent neural network or not. So in normal neural networks we don't create cycles, so this is a DAG, directed acyclic graph. Putting it all together, we can represent any kind of classification boundary. Like you see over here, using the sigmoid function we can create a square, and using squares, a set of number of squares, we can create a continuous boundary. So like this, in this what we are doing, we are trying to simulate square function. Numpy is not defined. Yes, bhai. So using these using the sigmoid functions, you see 1 upon 1 plus e to power minus z minus weight value z. So y1 y2 we define a starting point and ending point. We can simulate using the sigmoid function. Sigmoid function gives you, a sigmoid function is an s function. Okay, s function, it gives values like this. But using sigmoid function also I can simulate a step function. So this is a step function. So using this non-linear activation function, a non-linear output, you can simulate any kind of boundary. So whatever be the classification, you can have it your way. Like in this okay, I have some time left. So this training neural network is just like this. So this is the fundamental uh, mechanism which happens in all the neural network. What happens? We provide the input at input layer. So at input layer we have the input. So input is given in forward direction. So input is presented at input layer, then it goes to hidden layer. At hidden layer it does some computation. Some computation happens over here, and then output is passed on to next layer. In this case there is only one hidden layer, so I will assume that output is being passed on to output layer. So here also this goes, this goes, this goes, like this, all of these happens. Okay, so this goes over here, then this goes over here, and then these computation will happen, and this computation we produce an output that goes to output layer. Now output layer will take input from all the hidden neurons and then present an output. This is called feed forward mechanism, because the data is moving in the forward direction from left to right. At this moment when I have an output, a y is computed, a y is given, and f is computed, f of x is computed. So now this becomes your loss. Take it, sum it all, and divide by n. That becomes your mean squared error. Compute it, calculate the gradient of it. This, so suppose this is, remove it, this is called L loss. So del L upon del of W, the weight value parameter, and then you do a minus alpha. This becomes your gradient term. This gradient term is passed on to these neurons in the backward direction, so that all these weight values, associated with every edge gets updated. Okay, so instead of W's, they become W dash. And remember, at every edge, you have different weight values. So don't look at my writing. Although I have written W to everyone, they are W1, W2, W3, W4, etc. W5, etc. So all these weight values get updated. Now that is called backpropagation. Fine. So a lot of derivations are there because you have to find the uh, so this is what happens. You have Wij, new Wij is nothing but old Wij minus alpha del E upon del Wij. So E is the error or loss or cost function, whatever you call it. There is a slight difference between loss and cost, because loss is the loss of individual neuron, and cost is actually a summation of all the samples. So basic fundamental is the gradient descent. Although apart from gradient descent, there are other algorithms also, like Adam, RMS prop. All these are different ways of calculating of performing the backpropagation. Fine. So gradient descent is the simplest one. Using this, I have a very small example in which we create an XOR. We try to classify the XOR boundary. So XOR, you know that XOR has this property that on different values it gives 1, on same value it gives 0, right? Or I am wrong, I don't know, sorry. 1 1 will give 0. I think that is the case. Let me, if x and y are same, it gives 0. If x and y are uh, different, it will give 1. Okay, so that is XOR function. So let us let us create a very small quick neural network with this code such that we are able to find out decision boundary of an XOR function. Okay, so you see over here, for both x and y, how can we, okay, there is a question from Sapna that how can we decide which is the best optimizer function? Okay, rule of thumb, Adam is the most proficient one. However, still you start with Adam and then you can explore. There are not lot many optimizers. There are very few, set of 5 or 6. And the best thing is, that is what I tell all the participants of every FDP, you don't reinvent the wheel. Okay, हम कभी भी एकदम zero से start नहीं करते. That is why we do literature survey. When you do literature survey, you identify a paper which has executed, which has done something in the field of your research. So if that paper has done some preliminary research and of course would have published their results, that is an exceptional foundation or stepping stone that you should utilize. You first implement already established model, see what optimizers they have utilized, and then that becomes your baseline. From there you start modifying. So if anybody has implemented SGD, stochastic gradient, you implement that. If somebody has implemented Adam, you implement Adam, NADAM, so many RMS prop, whatever. So best thing is to start with whatever has already been implemented for the research problem that you are dealing with, and then from there keep on exploring. So you see, this is a very simple neural network with one neuron only, and I have used a tan hyperbolic tan h function, and this is the decision boundary that has been created. So you see, for x value, y value, uh, so x value, y value 0, it is producing this false. Okay, so both of them are 0, it is giving false. Both of them are 1, like this, it is producing so green, yeah, this green. So if both of them are 1, it is producing 0, false. If both of them are 0, it is producing false. If both of them are okay, and vice versa. So if one is 0 and other is 1, it is producing true. If this is 1 and this is 0, it is producing 2, right? Now, the final example in which you saw how we created a neural network, how we created a neuron. A very quick example of multi-layer perceptron, and this is multi-layer perceptron. Before the advent of deep learning, before people started calling neural network as deep neural network, there was a concept of shallow network. Rather, now it has become a shallow network before you start calling it a deep neural network. And that was multi-layer perceptron, because every neuron was also called, when it was hypothesized, it was called perceptron. It was not called neurons. Later people started calling it neuron, and there is a slight difference between neuron and perceptron. So there is, every node is called a perceptron, and since there are multiple layers of perceptron, this is also called as multi-layer perceptron. So I'm utilizing that notation, that nomenclature, to explain unto you how a multi-layer perceptron, a simple shallow neural network, can classify the handwritten digits. So for that, I have created a neural network dataset. Again, I'm using the MNIST database, that is our handwritten digit database. So for anybody who is starting with neural network research, this quotation holds true always. If it doesn't work on MNIST, it won't work on anything else. If it works on MNIST, it might not work on everything else. Okay, so this is a very good quotation, and you should always keep it in mind. So always start with MNIST, but don't be very hopeful that if it is working on MNIST, it's not necessary that it work on everything else. But if it doesn't work on MNIST, it definitely would not work on anything else. Okay, just like the pumping lemma of automata theory. You don't use pumping lemma to prove that a language is regular. You just use it to show that language is not regular, or probably not context free, kind of that. Okay, so we have our data set. We'll load it first, then we divide it into we see the shape. Training shape is 60,000, testing shape is 10,000, and then 28 by 28 indicating 28 pixels wide, 28 pixels long. Okay, we just plot it to see what an image looks like. So which image is that? This is the first image. Okay, now we try to see the distribution of the data set, and normally we want all the data categories. Like it has 10 classes, right? You have 10 digits, 0 1 2 3 4 5 6 7 8 9. So you have 10 digits, and all the classes should have equivalent number of samples. I'm not saying equal, equivalent. So it seems like all these bar graph shows that all the classes have equivalent number of samples. Now when we do categorical classification, we need to perform one hot encoding. What is one hot encoding? Remember in this example when I was telling you uh, in the neural network example, this animation, I was telling you that all these the ideal output is all of them must be 0, only the digit which I am wanting to have, like 7, must be 1, and remaining must be 0. So this is called one hot encoding, in which if I have to represent 7, I just don't give it 7. I give it this kind of vector, one hot encoded vector, in which the actual output, the desired output is 1, and remaining classes remain 0. Okay, so this is called one hot encoding. If it is any other digit like 2, then 2 will be 1 and remaining will be 0. Remaining will be 0, like this. I think there is a question. Sir, on what basis we decide number of layers in neural network? Okay, again a very good question, but see, these are all hyperparameters. Okay, we don't have any control. Had there been much time, I would have explained to you, because my code that I deal in class, I tried different shapes, different sizes of neural networks. So in that, I demonstrate that which network is working, which network is not working, to show to you that, okay, this is just hit and trial. Sometimes number of layers, you can create some layers which will work, and you increase the number of layer, that will not work. Okay, so these are called hyperparameters. Hyperparameters are those parameters which actually describe the model, because I have already used the term parameter. What are parameter? Those weight values are the parameter, and that is why this algorithm is called parametric learning algorithm. So parameters are those weight values. So I cannot use the same term again. So we use hyperparameter. Hyperparameter are the parameter which define the model, like how many hidden layers, how many neurons per layer, which activation function in which layer, which optimizer, okay, which loss function, which type of layer, what is the regularization technique that I use. All are decisions that a neural network developer has to make. So these are the flexibilities, or these are the deficiencies, whatever you can say. If everything is predefined, then what is the scope of research? तो आप रिसर्च क्या करेंगे अगर हर कुछ आपको प्रीडिफाइन करके दे दी गई? ठीक है, तो रिसर्च वही होता है कि आपके पास फ्लेक्सिबिलिटी है, यू चेंज few things and then you explore which one is giving you the best set of results. Okay. So ideally no
May
one
I
can answer
also,
that.
Dr. Munir,
Yes, sir.
also, so we need what the hyperparameters I can say. For running the code, like you have the error code, you have to fix these parameters. That's why the hyperparameters and parameters you are going to learn through the algorithm. So
Yes.
hyperparameters before running the algorithm you have to fix, and parameters through the algorithm you are going to learn. So that way you can differentiate.
Yeah.
That's I added what Dr. Munir is saying the
Yes, sir.
same
Yes, sir.
thing. Okay.
Exactly.
You can continue.
Fine. So I was discussing this one hot encoding. So remember I had told you what is one hot encoded vector. In our data set, the output are given as this kind of values. So if the first digit, first image is given, it's given as 5. But I don't need 5 because I have 10 output neurons. So I need a one hot encoded vector in which this 5 will be written like this: 0 0 0 0 0, 5 zeros, then 1, then 0, 6 7 8 and 9. Okay, so 0 1 2 3 4 5 6 7 8 and 9. Yeah, this is the one hot encoded vector for digit label 5. So this will represent to 0, then 1 2 3 4 and then 5 6 7 8 and 9. So one hot encoded vector for 5 will be this, for 0 it will be different, 4 it will be different, right? So that's my objective right now. I need to convert raw labels into one hot encoded. So see, these are encoded 1 0 0 0 0 1, then 1 0 0 0, then 4 is represented as 0 0 0 0 1 and so on. Okay, now we do dataset normalization. Our values, neural network prefers values between 0 to 1, small values. So what we have to do, we have to normalize the input values between 0 to 1. Why? Because these values are between 0 to 255. Remember, this is a grayscale image and grayscale ranges from 0 to 255. So what I'll do, I'll nothing but divide by the maximum value. So we divide by 255, all the values get into range of 0 to 1. That is normalization. Now we create a small neural network. Okay, and this is neural network. I have explicitly created it because it gives a very good result. Although this neural network is not immediately I got this thought, okay, I need to have these many layers, this is structure and these many neurons. It will, in my class, I converge onto this by several steps of hit and trial and error. So this is how I create this neural network. I randomly initialize using this random normal. I randomly initialize all the initial weight values with the standard deviation of 0.2. So init is an object with which I will initialize my initial weight values. The input is given as shape, input shape. Okay, so input is given like this. Have I flattened it? I need to flatten. Okay, flatten layer will be there. Flatten layer is there. Yeah, so 28 by 28 it looks like this. Okay, like this. I don't need matrix. I need one vector for input like this. So 28 by 28, this by this need to be converted to 784. So that is the job of flatten, will perform the flattening. Now my first layer, as I told you, remember the fully connected layer is also called dense. So I call the dense function, which will specify 32 neurons in first layer. Activation function is ReLU. ReLU is one of the activation function. I have not yet discussed, but due to lack of time, but you can very well see that ReLU is nothing but very small, simple function, max of X and 0. Okay, X and 0. Flatten is just to convert a matrix into a vector. Okay, I have the image in 28 by 28 shape, so 28 height, width, and 28 height, 28 pixels in width and 28 pixels in height. So this looks like a matrix. Flatten is nothing but converting that into, it's a reshaping uh, function which converts it into 784 values. That's it. Okay, fine. So max, this is ReLU function which gives you maximum of the input or 0. So its curve looks like this. Okay, so 0 or max. So this looks like this. So this is ReLU function. ReLU function is very good function for neural network. Instead of sigmoid, people have started ReLU somewhere, some layers. So first layer has 32 neurons, second layer has 64 neuron, third layer has 128 neuron, fourth hidden layer has 256 neuron, then fifth hidden layer has again 256 neurons, and then finally I have the output layer which has got 10 neurons. Okay, so let me run this. Okay, so this is defined, this is defined. Now and finally, you remember probably in the last class also I had told you we compile the, once we have created the architecture, this is the architecture that we have. After this architecture we need to compile to see everything fits properly. So in that, since it is a categorical classification, the loss function we are using is categorical cross entropy. The optimizer we are using Adam. So again, I'm starting with the best optimizer that there is, and matrix for testing whether how good the model is accuracy metric. So I compile this function and then I create the model, and then using the fit function I'm actually training it. So you see, okay, it will take some time. In the meantime, you can ask any question in the time it is training.
Okay, participants, if you have a question, you may unmute and ask.
And you
Anybody
see
have
every
any question?
epoch it is also demonstrating you the accuracy. See, 94% accuracy, 94%, 94.81, and this accuracy is continuously gradually increasing also. Any question?
Does anyone have any question, please?
Hello.
Yeah.
Yes, yes.
Hello. This side Shalendra speaking.
Okay,
Actually, sir,
Shailendra.
I want to know that accuracy is depend on epoch and iteration also or not?
Yeah, definitely. Definitely, because you see in the linear regression I had shown you, we had fixed number of iterations as 10. Okay, you can go on more number of iterations, but at some point of time you have to stop that. Okay, if the error is not decreasing any further, that is the point when we stop the iteration, the number of epochs. So number of epoch definitely matter. If I, instead of 20 epoch, had I run it for 2 epoch, then it would not give me 90% accuracy. You see over here, the first epoch gave me 50% accuracy, right? Second epoch gave me 90% accuracy. Third epoch increased it to 92%. Fourth epoch increased it to 93, and gradually it is increasing. So number of epoch definitely matter.
Okay.
Okay, Rohit has a question. What is kernel initializer? See, kernel initializer is the initializer with which we are initializing our weight values, the first set of weight values that you put on those edges. That is the job of kernel initializer. And for that, we do it like this. We use this function random normal. So we utilize the random number from the normal distribution, use normal distribution, and the standard deviation for that has to be 0.02. So this is how we initialize. Uh, with this, we get the random values and we initialize the weight values. I think it has completed, and finally it has given me 96.65% accuracy. Okay. So this is a simple, very simple neural network in which I have not used any kind of convolution, any kind of recurrent. However, I have used the dropout. Yes, dropout is something that is a regularization technique. Regularization, I think you will discuss, but very quick uh, uh, intro to
We also
regularization.
discuss in the one more lecture in the deep learning system will discuss.
Yes, yes. So, but very quickly, if I have to talk
Quickly,
about
yes.
dropout is nothing but switching off some neurons. Suppose uh, this is a fully connected neuron, fully connected layer. Okay, and let me use some existing diagram. My diagram is very bad. Yeah, just take this one. Suppose I have this neural network, and dropout means I switch off some hidden neurons. So if I switch off some hidden neurons, it means I switch off this neuron with a probability of 0.5. Means I toss a coin, or I generate a random number between 0 to 1. Okay. If number comes out greater than 0.5, means let's say 0.6, then I will switch off this neuron. So any connection passing through this neuron will be switched off, this edge will be switched off, and this output neuron will get input only from these two neurons. Okay. Okay. So if I don't switch off this neuron, let's say I do this on every neuron dropout. So over here, I toss a coin, let's say head or tail. If I get head, I will switch off. Over here, I toss a coin, I get tail, I will not switch off. Over here, I get a tail, I will not switch off. So it means one neuron is switched off, two neurons will pass the result to, or the result, their computation result to next neuron. Other than that, it might happen that this neuron produces a tail, this neuron produces a head, and this neuron also produces a head. Means two neurons are switched off, only one neuron value is going over here. Why do we do it? We do it to make every neuron robust, to we make the neural network robust. So what is happening is that we say that if neuron is not able to bear the load of its fellow neuron, then that neural network is not robust. So suppose you have a team, and in team, if one person takes a leave, then other members of the team have to bear the responsibility of the person who has taken leave. Okay, so the same thing happens over here. We don't want any single neuron to learn too much. We randomly drop it, we switch it off, and the remaining neurons stand up to the occasion to learn what this neuron was learning. Okay, it means we are training the neural network to live without this neuron. So there is a possibility that this neuron is not present. So I am asking the neural network to learn to live without this neuron, because I don't want any single neural network to neuron to learn too much. So that is a regular.
Sir, then what is the benefit of, sir, excuse me?
Yeah.
Yes.
Sir, what is the benefit of then placing these many neurons in the hidden layer if we are not we don't want to train all the neurons equally?
No. We are training all the neuron, but I'm not wanting my neural network to be dependent on any given neuron too much. That is avoiding the overfitting. So you see, there is a fine balance between underfitting and overfitting. Okay, I'm I'm wanting my team to be very efficient, but I don't want to be dependent on a single member too much. कि पता चला कि डॉक्टर केपी सिंह पर ही everything is dependent on Dr. KP Singh, and if Dr. KP Singh has to take a leave, sudden leave, everything crashes down. That should not happen. Dr. KP Singh.
Sir, then what is the probability that every neuron get trained?
Every neuron will get trained if you keep on randomly switching off some of these neurons.
Sir, but that is a random function, and that random function may not get select a particular neuron.
That happens.
In one epoch, one neuron may not be trained, but in the next iteration, that neuron may be used. Again, randomness. It will not be for whole process. It will for one epoch. So in each epoch, sometimes it may, sometimes it may not. So it is for the spoon fitting.
So we have 20 epochs.
Okay,
In
sir.
one epoch, it may be activated. In other epoch, it may get deactivated. Okay. And
And
remember the probability of 0.5. Normally, we keep a probability very low. So over here, I think our probability was 20% only, right? So we keep it very low.
Sir. Thank you.
This is also one hyperparameter. This dropout.
This is also one of the hyperparameter, exactly.
That we have to fix before the running value.
So you see over here, the first layer has dropout of 10% only, 10%, 20%, 30%, 40%. Okay, I haven't even touched 50% in any of the layer. Good question.
Okay. Anyone else also have a question? In this way, I would like to
reach the end of this lecture. So if you have any question, you can ask me regarding anything.
Yes. Okay.
I think that's all, sir.
So we may close now, Dr. Muneendra?
Yes, sir, definitely.
Okay. So thank you, Dr. Muneendra, for sharing this hands-on session and basic concepts on the Google Colab. And I'm sure that if the participants, those who are not aware, even those who are aware from the past with Google Colab, you start working on that. And many hands-on and data sets and many, you can say, guidelines are available online. So you just start working and you just may learn. We will be very hopeful that if you just start working on Google Colab using the existing tool, it will be great and you will start learning, those who are not doing. So I would like to thank Dr. Muneendra for just giving all these basics, how to start and how to work and how to even he had discussed about the regression, perceptron and development of how the neural network has been done. So with this, again, I would like to thank Dr. Muneendra for sharing valuable opinion and their lecture and giving valuable time, more than even the time 1 hour 30 minutes. They just spared more time on that. So again, thank you, Dr. Muneendra, for sparing time. Thank you.
Thank you, sir.
Again. Thank you. So participants, well, I thought you have enjoyed this session. So it's now the break for the lunch, and we will meet at start 3:30 now for the next lecture, and it will be on the application of machine learning on some streaming data and other applications. So be tuned, and then we will meet again for the next discussion. Thank you, and till then, enjoy. Thank you, Dr. Muneendra. We will meet again.
Okay, sir. Thanks. Bye.
Thank you.